Okay, so yeah, so today we will discuss about the hard magnetic materials. So when I say about hard, means they have high coercivity. That means high magnetic anisotropy. Okay, so these are the materials which have very high magnetic anisotropy. So high magnetic anisotropy means, so if I look at the structure, the crystal structure, the arrangement of atoms, okay. So if I have the crystal, so high anisotropy means I will have, so these are the directions, like X, let's say this is my Z, this is X, and this is Y. So the magnetic or magnetization would prefer to stay along one of the axes. So it could be X, Y, Z, or can be some diagonal like this, or any. So these are the possible directions in the crystal, and the magnetization would prefer to lie along one of the directions. And then, if the anisotropy is high, that means so this energy, so which I wrote in the beginning of the class, this is k sine square theta. So this is defined by this anisotropy energy. So this k value will be high. This is high. Okay. So the value of k is high. So what we are talking about is materials which have only one single direction, where the magnetization, there is only one direction along which the magnetization will lie with a, and it is very difficult to rotate the magnetization into any other direction in that crystal. So that is this magnetic anisotropy. Okay. So now the question. So there are a lot of things with this hard magnetic materials. So particularly two applications which are or mostly these are the two applications of hard magnetic material. So one is permanent magnet, and the other one is for magnetic recording. So like what we have is a hard disk drive. Okay. So these are the primary applications of our hard magnetic materials. So we will discuss it later. So first we discuss about the permanent magnets. So one I talked about permanent magnets. So if you remember, for the permanent magnets, so if this is, let's say, the hysteresis loop. So I told about a figure of merit. Okay, so the figure of merit. So that is known as a BH max. Okay, this is the energy product. Okay, and so typically this energy product is measured in the second quadrant. So this is my V axis and this is my H axis. So this is measured in this quadrant, in the second quadrant. So why it is like that? So this is your magnetization curve, right? So when you start with the initial magnetization, you magnetize, and when you reduce, so this part is known as a this part of the curve is known as a demagnetization. So it is a demagnetization curve. Okay, so this is a demagnetization curve. So why this quadrant is interesting? It's because so this curve, the shape of the curve tells you. So basically, from here you can get the information of what is the residual, the remanence, what is the coercivity, and the shape tells you how fast or how slow the magnet will become demagnetized. So if I want to demagnetize the magnet, so demagnetize means it will have zero magnetization. So if I want to achieve that, how I do that? Is it difficult or easy? So this shape of this curve tells you that. And for permanent magnet, what you want is like it should be magnetic as long as it is. So it should not be disturbed by any external field or any disturbance or any stray field or any fluctuations, thermal, magnetic, nothing. So that is the best permanent magnet. So that means this curve, the best curve it is, the difficult it is to demagnetize, that will be the best permanent magnet. So how do we? So there are many things related to this while designing permanent magnet. So I will discuss only one part, that how development of materials led to better permanent magnets. So to understand that, we do take a simple magnetic circuit. Okay. So we'll come back to this BH max in a moment. Okay, so let's take a magnet, something like this. Okay, so this is like a typical magnet in motors, or like when you rotate rotating magnets when they are used, or you want to rotate some coils inside it. So this is our magnet. So we call this length as, this is the gap. Basically, this is a gap which is filled by air. Okay, and what we want is, we want the magnet to produce a magnetic field. So here the magnetic field is Eg. Okay, this is the magnetic field. It produces within the gap. So what we want, that Bg, which is equal to mu naught Hg, should be it should be as high as possible. So that is the best magnet we can have. So the magnet is designed in such a way that when it produces a magnetic field within the gap, so which is this is the magnetic induction, and this is the magnetic field it produces in the gap, so that should be as high as possible. So now, of course, the magnetization, the magnet has certain magnetization. So this will have a magnetic induction Bm. So that is of the magnet. Okay. So Bm, which is a magnetic induction of magnet. But if you remember, so this, due to this, if there is no external field, so if I take magnetic material as a magnetization like this, so the internal field will be, there will be an internal field which is opposite to this magnetization, which is known as your demagnetizing field, HD. Okay, so each magnet, any magnet which has a magnetization M, so will always have a demagnetizing field inside it, so which is opposing this magnetization. This is the demagnetization field. And the sample always, the geometry, you choose the geometry in such a way that the demagnetization field is minimized. Okay, so that means you can. So in this case, the magnetization would prefer to lie along this axis rather than along this axis. So then the field HD will be small. Okay. So this magnet will also have a demagnetizing field, so which will be the opposite to the magnetization, which is, let's say, in this direction. So HM we call the demagnetizing field associated with the magnet. So and we say, let's say, LM is the length of magnet. Okay. So now we do a simple use Maxwell's equation. So if we use Ampere's law, so let's say we assume that this is a magnetic circuit. So what we have here is, we can say this is our magnetic circuit. So when we calculate from Ampere's law, so since there is no electric current, so we can say around this complete whole circuit, H dot dl will be equal to 0. Okay. So if you simplify that, so we can write it down as, so we have Hg into Lg minus Hm into Lm will be equal to 0. Okay. So this is Hg is a magnetic field in the gap and the length Lg, and we say Hm is in the opposite direction. So this should be equal to 0. Now we can also take consider the magnetic induction. Okay, so this always has to be a continuous field. So we assume that there is no leakage of magnetic field. So whatever magnetic field inside, B field inside, so that the same thing exists in the gap here, and that means your del dot B is 0, right? So if you convert it into your, so the flux, that means your flux would be constant. So this is your B dot ds, and over the surface. So the flux will be, so in this case the flux will be, let's say this is our equation 1. So the flux will be Bg into Ag. So we can say Ag is a cross-sectional area of the gap here, will be equal to Em into Am. Because the same flux, whatever flux we have here in the gap, the same flux also should exist. So there is no, because of this del dot B equal to 0, this condition that the magnetic field lines have to be continuous. So the flux has to be conserved, and this is how we can write down. So Ag, you can write down, is a cross-sectional area of gap, and Am is cross-sectional area of magnet. So this cross-sectional area is, let's say, this section like into the board. Okay, so that is the cross-sectional area. So this, let's say, we say our equation number 2. So now if you multiply this, so what we get? So we multiply equation 1 into 2. So what we have is, so H G B G into A G into L G will be equal to B M H M into A M into L M. Okay, so this is the, so what we can write simplified further. So we can say this is H G B G. This is the volume of the air gap. Okay, and this is your Bm into Hm, and this is volume of your magnet. Okay, so again the Bg is nothing but mu naught Hg. So this again we can write down as, so that implies this will be mu naught Hg square into Vg will be Bm Hm into Vm. Okay. So this equation, this term is something like the energy stored in the gap, right? So this is mu naught Hg square. This quantity is the energy stored within this gap in the volume Vg. And immediately what you see is it is related to the product of B and H. So it is the product of B into H of the magnet, which is producing Hg. So now if I say for a given volume, so if I have a given volume Vm, if I want to produce the highest, I want to get a highest or like a maximum field Hg or Vg, that is what I want. Okay, so I want maximum field as possible here for a given volume. So what I have to do is I have to design the magnet in such a way that the Vh value is maximum. So if when we remove this one, so if Vm into Hm is maximum, so then Hg is maximum. So our goal is to get maximized Hg because that is the best permanent magnet. That is how we can get as much field or magnetic induction due to the permanent magnet. That means we have to operate the magnet at when the B and the product of B and H of that magnet is maximum, and that's why we have this BH max as a figure of merit. So this is where this BH max calculation of the concept comes from. So another thing is, look at this Vm. So what we say is, we said we have constant volume Vm. So now, so how the role of material comes into the picture here. Okay. So if I want to produce, let's say, some value of Hg. So let's say I want Hg is equal to 1 Tesla. Okay. So I take, so two materials I take. So material 1, magnet 1, Vm1, Hm1 into Vm1, and so both are going to produce the same one Tesla field. Okay, so material 1 and material 2. So material 1 has volume M1, material 2 has volume M2, and so on. So if I design a material which has a higher this BH max, okay, so let's say this BH max 1 is less than BH max 2. So this BH product for the material 1 is less than material 2. So that means if I want to produce a 1 Tesla field, also I should say this is mu naught Hg, so Vg I want. So if I want a 1 Tesla field, so in that case, and if BH for material 1 is BH max is less than that, so in that case Vm1 will be better than VF. Okay, so that means if I take a small volume, small amount of material too, I can produce 1 Tesla field with that. But if I use another material which is low VH max, I have to take a larger volume, bigger volume. So this has a big consequence, because nowadays we are all talking about miniaturization. So you are making devices as small as possible. Okay, so that's why materials which have high BH max. So the higher the BH max of this product, energy product, higher the energy product, you can take even a smaller amount of that material, a smaller volume of that material, and you can get a very good or a high field. And you can miniaturize your devices, and that's why this so research into material which can give very high energy product is quite necessary. So I will list down certain materials. Okay, so the first material which was actually used as a permanent magnet is called alnico. So definitely this is a sort of aluminium, nickel, and cobalt, but it has an iron with considerable amount, 58% iron. Although iron does not come into the name, because the first one actually which was made was with aluminium, nickel, and cobalt. But then later on, people used they used iron, they added aluminium, they added copper. So many other things were added, like when you make a alloy, but the name still remains alnico. Okay, so this was like, let's say, around 1930s. So the material, then the next, like in 1950s, there are two different materials. One is strontium ferrite or barium ferrite. So these are ferrite materials. So yesterday we talked about soft ferrite. So these are hard ferrite, so which came into 1950s. So this material was developed, was synthesized for the first time in 1952, and then this has much higher pH max, or the energy product, compared to alnico, and that's why you can even get the same amount of field, you can reduce the material. And in 1970s, so then came this rare earth permanent magnets. So these are like SN cobalt 5, SN2 cobalt 17. So these are the different compounds, and nowadays this is this neodymium iron boron, that is so sometimes short form of this. So this is used quite a lot nowadays as a permanent magnet material, and again the BH max is much higher compared to these two permanent magnets, and that is how the research in materials actually led to new discovery or synthesis of new materials, which led to better energy product. This energy product, which is BH max, so that increases like for NDFB, that is the maximum. Okay, so far, but again, some new material can come which can have better, even higher pH max. So you never know. So this is how the role of materials into development of permanent magnets play a crucial role in developing new permanent magnets with better energy product, improved energy product, so that you can use smaller volume to get the desired magnetic field. So the unit here, this is as it is energy. So in CGS, it is mostly is written in megagauss in Oyster. and in SI it is this from kilojoule per meter cube. So you can look in the first lecture, I showed some graphs. Okay, so there you will see the comparison how the pH lags for different materials, for aluminium, for ferrites, and for rare earth, how it varies, changes. Okay, so this is the thing about one part of hard magnetic material, and then we will consider in the next session we will talk about application in recording medium. So how that plays a role. Okay. Any question? So is it clear? So if you have any questions or anything. So I would suggest that you go through the video lectures as much as possible, because sometimes so you will know if you skip something in the class. So if you hear it, so I tell things which I might not write on the board, but they are also important for the course. So you should go through the video lectures, just listen to that, and yeah, so we'll then meet in the next session. Okay, so we can stop the recording now, and then we will meet.